Dad, they're here already. They're already here, Dad. You better come. Okay. Thanks, Snow. So this is problem 4. Let's take a look at problem 4. Here we've got a point on the plane in 3 space, and we've got a normal vector to that plane. So just a point and a normal vector. And then we want to find the plane that contains that point and is perpendicular to that normal vector. The first question is, find the point normal form of it. So this is the Cartesian form of it. And this point normal form is, we are set up to do that. So the point normal form is that if you take x1 minus 1, x2 minus 2, x3 minus 3, dot product with the normal vector, you are going to get 0. So that is the point normal form of the equation. It is a vector equation. No parameters involved, so this is not a parametric equation. We're going to ask about that later. And the second thing I asked about it is find some points on it. So to do that, I'm going to multiply this out and get the expanded Cartesian equation. So x1 minus 1 minus 2 times x2 minus 2 plus x3 minus 3 equals 0. Collecting the variables on the left, x1 minus 2x2 plus x3 equals, let's see, minus 1 plus 4 is 3, minus 3 is 0. Wow, did I make it an easy one? Goes to the origin. Minus 1, minus a minus 2 is 4. 4 minus 1 is 3, minus 3 is 0. Yeah, so this looks like the Cartesian equation, not written in vector form, but just written out. And we can use this equation to find some points, some other points on the curve, on the plane, on the surface. So let's just do this. Points on. And over here, we'll find directions again. When in doubt, you can always do this process to find all of the equations. We know that 1, 2, 3 is on. So let's set x1 equal to 0 and x2 equal to 1. Then that should allow us to solve for x3. So 0 minus 2, x3 is 2. I'm going to set x2 equal to 0 and get another one. So that means that x1 and x3 are negatives of each other. x1 plus x3 has to be 0, so 1, 0, minus 1. Setting x3 equal to 0, we'll say that x1 minus 2x2 is 0, so if x2 is 1, then x1 would have to be 2 in order to satisfy this equation. So we're just plugging and chugging and finding some points. Letting one of the variables be 0 usually is an easy way to do it. Calling these points A, B, C, D. Robert did this in class. That was a good idea, and it makes finding directions pretty nice. AB then is one of the directions of the plane because it is the vector between these two. So minus 1. Minus 1, and minus 1. We also could have used 1, 1, 1, because if you have a direction of the plane, any multiple is also a direction of the plane. AC, 1 minus 1 is 0. 0 minus 2, minus 1 minus 3. AD is 2 minus 1, 1 minus 2, 0 minus 3. And we can find another one. I don't know. How about BD? So using these two, 2 minus 0, 1 minus 1, 0 minus 2. So here are a bunch of points and a bunch of directions that are on this plane. And this little pattern here, this table, will allow us to get any of the equations. Find a parametric equation for two lines that lie entirely on Eleanor. Two lines. First of all, point B, problem B, find three very different point direction equations, parametric functions for this plane. So let's find those, because those are going to be interesting to us. So we're going to have a P1, a P2, and a P3. Each one will be a function of S and T. Each one will use a point and two directions. So for the first one, we'll use this point and maybe these two directions. They're linearly independent. So that would be the point 1, 2, 3, plus S times minus 1, minus 1, minus 1, plus T times 0, minus 2, minus 4. This should be a plus. The second one, let's see, let's use this point and these two directions. So 1, 0, minus 1, plus S times 1, minus 3, minus 1, minus 3, plus T times the second one, 2, 0, minus 2. And we could find another direction. I guess I've used up all four. Maybe I'll reuse one of them, or use pairs here, but let's use a different point. Let's use BD and AB for this. So the point is 2, 1, 0. Plus S times 2, 0, minus 2, plus T times minus 1, minus 1, minus 1. So there are three pretty different parametric functions, each of which has its range being Eleanor. Now the next part asks, find parametric equations for two lines lying entirely on Eleanor. So the situation is that we've got Eleanor, this plane here, and I want two lines, maybe this one and maybe another one. We want two separate lines that lie entirely on Eleanor. Now lines only have one parametric equation. So in order to get a parametric equation for a line, we need a point on it and one direction. So let me give the first line, L1 of just T is equal to, let's use this point, 1, 2, 3, plus T times, and now we need a direction. Let's use this direction, 0, minus 2, minus 4. Now you can see that this line is inside, I mean, it's contained in this equation. You just take the free variable S and freely make it 0, you get the equation for a line. Or if you take the free variable T and make it 0, then you get an equation for a line. Or if you take the free variable S and make it exactly the same as the free variable T, then you could factor out that t and you'd get another line. So every one of these lines can be obtained by manipulating the free variables that are in the equations for the plane, and you can do that for any of them. So a second line, L2 of t, a point on 1, 0, minus 1, plus t times. We can use either one of these directions, 2, 0, minus 2. So we could have used the other one, even though it multiplies the s. This is a direction within the plane, the range of that function, so we're good. So here are two lines, both of which lie in Eleanor. Here are three equations for Eleanor. She's got a lot of names. Find symmetric equations of two lines, each of which is orthogonal to Eleanor. So now, now we need some stuff here. I'm going to erase this. And I've forgotten the Cartesian equation for Eleanor, but I'm going to get that because I'm going to use that little trick we did in the last problem. The little trick is to use those coefficients. In the last problem we had, the point on was 1, 2, 3, and it was orthogonal to 1 minus 2. So x minus 1, x1 minus 1, x2 minus 2, x3 minus 3. If you guys would be here, I'd ask you how to do this, what we got the last time. 1 minus 2, 1. This is normal. So what we need here is this normal vector because we wanted the symmetric equations of two lines, each of which is orthogonal to Eleanor. So we want lines with this direction. So line 1 and line number 2, we'll need a point on in either case. And we'll need a direction. And the direction in either case will be this n. 1 minus 2, 1. And the point on does not have to be on Eleanor, because as long as a line is perpendicular to this plane, it will intersect that plane. So these will be lines that are perpendicular to Eleanor just by the mere fact that they have this as their direction. So, but we do need some points on. Let's take an easy one here, 0, 0, 0, and 0, 0, 1. So these will be parallel planes, and they will not be the same plane because of the points that I've chosen. Have to be a little careful there. The first line, L1 of t, will be the point on 0, 0, 0, plus t times 1 minus 2, 1. So is the equation t times 1 minus 2, 1. And L2 of t will be the point on 0, 0, 1, plus t times 1 minus 2, 1, which is equal to t times 1 minus 2, 1. I guess this is good enough. Just leave it like that. So those are the two normal lines. Find a Cartesian equation for which Eleanor is the graph. And if we multiply this out, we're going to get that Cartesian equation, and we already did that in the beginning in order to find those points. This, by the way, is a Cartesian equation, but it's a vector equation because it uses vector operations and Cartesian variables. So this one was x1 minus 2x2 plus x3 equals 0, I think. We got this. And the very last part, find a Cartesian equation for a plane that is parallel to LNR. So a Cartesian equation for that plane would be just change the intercept. So rather than equal to 0, make it equal to 1. 0, 0, 0 doesn't satisfy this, it satisfies this. So these are parallel planes, or this could have been 14, or 14.3, or 14.3 times pi to the e power. Just any constant here will make that any change here. These are parallel planes because these coefficients are the same. They have the same normal vector. 1, minus 2, 1 is normal to all of them. That's it. Problem 4. And get your Mathematica running. Some of you didn't have the Mathematica up and running. If you are on campus is pretty easy. If you are off campus, then, and you didn't register your copy of Mathematica and get a code to get it working, you'll have to do that. Check the syllabus again. We can talk on Friday. See you soon.